Okay, here's another problem. So in fluid dynamics, you're going to get problems where you've got fluid flowing, so you know it's dynamics and not statics. But the dilemma is going to be which equation to use. Do you use Bernoulli's equation or PHYS law? So let's read the question and we're going to figure out which one now. In each of the pipes shown below, well, first of all, we look at the picture and we see tubes going up and down. That means that it's going to be Bernoulli's equation. Okay, that's giving me the idea that it better be Bernoulli's equation, because PHYS law is just for horizontal tubes. Like, you're going to squirt some milkshake out of a straw. That straw is horizontal. There's the atmospheric pressure on the output. There's the pressure that you're applying on the input. You get a volume flow per second. Once you see tubes going up and down, once you see tubes changing diameter, it's going to be Bernoulli's equation. So let's look. In each of the pipes shown below, the area is 5 centimeters squared, okay? And flow of the fluid is to the right. Which configuration would have the largest pressure drop across the pipe? The fluid density is 1,000, I guess it's water, and eta is equal to 0. Makes sense. So Bernoulli's equation, you don't have any viscosity, okay? So I'm going to write down Bernoulli's equation up here at the top. Oops, that always happens. Nope. Maybe I have to do something here. Yeah. P1 plus rho GH1 plus 1/2 rho V1 squared is equal to, okay, I'll say a constant. So we're going to use this equation, and we're going to try, okay, I'm not going to say constant, I'm going to say the right thing. P2 plus rho GH2 plus 1/2 rho V2 squared. So that's Bernoulli's equation. We're going to be using it for these three cases, and we're going to try to compare the pressure drop. So what's going to be the difference between P2 and P1? So let's look at this equation on the first problem, A, number 1. I'm going to write down, rewrite it, GH1. So, yeah, plus 1/2 rho V1 squared is equal to P2 plus rho GH2 plus 1/2 rho V2 squared. So we see a height difference. I don't like working with minus signs if I don't have to. So I'm going to call this, height equal to 0. I'm going to be measuring from here. Okay? What that means is that the first height is 10 centimeters, and the second one is 0, right? So we're going to write down P1 plus rho G 0.1, right? So, write it down, 0.1 meter, right? Plus 1/2 rho V1 squared is equal to P2, and this is going to be 0, plus 1/2 rho V2 squared. Okay? I could put in plus 0 if you like. Plus 0, so you know that where that went. Okay? Because the height is 0 on that. Okay? Next, the velocities. What are we going to say about the velocities? They didn't tell us the velocities. So the areas give it away. So the flow equation says Q is equal to area 1 V1 is equal to area 2 V2. So if in the tube the area doesn't change, then the velocity doesn't change. I don't care whether it's going uphill or downhill. Okay, in Bernoulli's equation, it means that the velocities are the same. So if the velocity is the same, these two terms cancel. It's just like when the heights are the same, we can cancel those two height terms. Or when the velocity is the same, you can cancel the velocity terms. So we rewrite it. We write down P2 is equal to P1 plus rho g over 10. Okay, let's plug in the numbers. P1 is equal to, P2 is equal to this plus 9,800. Okay, because it's 1,000 the density, gravity is 9.8 divided by 10. Boom, I think I got it right. Or did I multiply by, you know, I made an extra step. Just like that, okay? 980. So that's not a pressure drop, it's a pressure gain. P2 is greater than P1. Let's try the next one. The next one, P1 plus rho GH1 plus 1/2 rho V1 squared is equal to P2 plus rho GH2 plus 1/2 rho V2 squared. So what do? The height stays the same. And because of that, the height terms cancel. We solve for P2. P1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared. So what can we say about the velocities? Well, we can say that Q is equal to area times velocity 1 is equal to 3a times velocity 2. And they're all equal. So V1 is equal to Q over A, and V2 is equal to Q over 3A. Makes sense? I plug those in. P1 plus 1/2 rho, I can put them in parentheses, I guess. Oh, it's squared. So we've got to say Q over A squared minus Q squared over 3 squared A squared. Now, look, I plugged it in. I did some steps at the same time there to save some space. If you were to do it, maybe you would do the algebra a little differently. I can factor out the Q squared A squared rho Q squared 2 A squared. And then this is going to be like, that's a 9. It's going to be like 1 minus 1 over 9. Okay. Finally, P1 plus rho Q squared over 2A squared 8/9. Again, P2 is greater than P1. But they didn't give us the flow, and they gave us the area, but they didn't give us the velocity, so we can't figure this one out. Let's look at the third problem, the third part. So in this one, P1, I'm going to spell it out, rho G H1 plus 1/2, slowing down, rho V2, 1 squared. Is that? Is equal to P2 plus rho GH2 plus 1/2 rho V2 squared. Okay, what happens to the velocity in this problem? Does it increase or decrease as it goes through the tube? Well, the tube has the same diameter, so just like in part 1, the velocities stay constant. So the second term, the third terms cancel. What about the height difference? H1 and H2 can both be called 0 or the same. It doesn't matter. They cancel. So you get P1 is equal to P2. Da, da, da. So what happens is in part 1, the pressure increased by 980 Pascal. In the second one, it increased by a funny formula there, 8 nines, blah, 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 but it increased, okay? And third one, the pressure actually stayed constant, okay? Because it's not going up and down, and it's not changing velocity, so the pressure stays the same. Let's see. Which configuration would have the largest pressure drop across the pipe? Pipe 1? No. Pipe 2? No. Pipe 3? That's funny. The one that has the largest pressure drop is going to be C. Pipe 3, because the others actually have pressure gains. That's a tricky problem, huh?